Okay, is everything clear so far? At least you get some gist of it, right? Now.
Yes, sir.
Okay, so take a deep breath, relax. Okay, now I'm just, whatever that I have talked earlier, I'm just going to put them into different slides. So dim0, remember it is not going to use contiguous memory locations. So it could pick any memory location. It doesn't bother about this, discontinuity, all these things. So it stores the number at some random memory location. So that's why we use .item to call that one. Okay. But when you create one-dimensional tensor, when you call this torch.tensor, okay, you are passing this 0.1, 0.2, 0.3. Now I am creating a one-dimensional tensor. So by looking at this bracket, we can say the dimension. It contains only one bracket, so it is a one-dimensional tensor having three elements, each of dimension 0. Okay, of course we don't bother about this, but just for the information. And in memory location, all these elements are stored in a contiguous memory location, right? And then the storage is, of course, it's a contiguous memory, and the stride value is 1. So what does that mean? The stride value is 1. So when I put actually x of 2, right? I know this is an array stored in a memory. So I have an index. Of course, we have some hexadecimal representation for the index. In fact, when you refer to the memory location, so whatever the index I have, if I pass something here, I just add that value, and I will go to the respective memory location. Okay, so accessing an element, we say it's a big O of 1. It's a constant access. Okay, so that is what we want. So when you in fact put x of 2, it goes there and brings this value 0.3 or whatever there in this memory location. Okay, so this is fine. Now, yeah, so that's why the stride value is 1. Now we have two-dimensional tensor. Okay, so typically we tend to think of two-dimensional tensor as a matrix. That is absolutely fine. Okay, you can think of two-dimensional tensor as a matrix and each element as rows. Okay, but it may not be helpful when you go with high-dimensional tensor. Okay, you tend to mix up a lot of things. We can, why am I say it is two dimension? So I start with the inner mode dimension, which is 0 dim. So I can see there are three elements in three zero-dimensional element packed into one-dimensional arrays, right? Or one-dimensional tensor. Okay, so this is one pack, and then this is pack 2, and this is pack 3. And then I am encountering the outermost square bracket. Okay, which means when I add square bracket into the tensor, which means I am creating a new dimension. Okay, so I have outermost square bracket, which is one dimension, and within each of I have 3. So essentially, I have outermost square bracket, which I have created one dimension. So within that, I have 3 square brackets. Okay, I don't really bother about the elements inside the square brackets. So I would say the outermost dimension, okay, or dim1 or whatever. Okay, so it contains 3 elements. Okay, and then as you know, the shape has to match. Okay, if I look at this element, if it is of size 1/3, then all the rest of the elements should be of same size. It cannot be of different size. Okay, so from this I can know 3/3. The 3 refers to dim 0 and this one dim 1. Okay, so I often tend to confuse this, but of course by looking at the code we can fix this. Okay, now internally how these elements are stored. Internally we don't bother about the square brackets at all. We just look at the numbers. Okay, and then since we are saying we are following row major ordering, okay, so we say these are all rows, and then we simply store all these elements in the same order. Okay, so in a memory location. Now I can access the element x of 1. Remember, it is now a two-dimensional tensor, but I am only passing single value to this x. Then what will be the output? It returns what? Whether it throws an error or it returns something.
0.2.
0.2. Okay.
I think the 0.4, 0.5, 0.6 vector, that one-dimensional tensor is written.
Okay. So what is the interpretation of this? So the interpretation is that I am accessing an element. I know it is a two-dimensional tensor, but I am just passing the argument for only one dimension. I am not passing the argument for the second dimension. Okay. In turn, it means that this is I am just pass. The dim zero contains three elements, right? Packed something like this. So what I am accessing the first element in dimension 0. Which is the first element? This is the zeroth element. Whatever the elements within the square brackets, everything is now in 0 dem. And then this is 1 and this is 2. So it will take this square bracket and prints whatever inside it. Okay. So if you look at that, this is the zeroth element in dim 0. This is the first element in dim 0. This is the second element in dim 0. So all these are first element of dim 0, right? So it will take all these element, and also remember that when it returns, we lose one dimension. Okay, now it is no longer two dimension. It is not kind of 1 by 3. Yeah, initially it is 3 by 3. It is going to be 1 by 3, I guess. Yeah, it has to be 1 by 3 by the way. Yes. Okay, so for in the first place, now you got this right. Why it returns this 0.4, 0.5, and 0.6, all these three. Is everyone comfortable with this answer? Why it returns? Of course, you can execute and see. Also, since I created this tensor, I can see what are all the stride values. There is a logic behind why this is 3 and why this is 1. But let's say I access it using this attribute x dot stride, then I get this number 3 comma 1. Okay. So using the stride value also, you can justify why this 0.4, 0.5, 0.6 is returned. Okay. Visually, we can see this returns the first element of 0 dimension. Okay, which is 1 by 3 vector. Okay, but internally how it happens? Internally it doesn't know the boundary of this square bracket. What we have internally is this n contiguous element stored at n contiguous location. Okay, so that is where we have to make use of this stride information, right? So try to understand the concept of stride for this one dimension, one dimension or two dimension. Later, you can just ignore if you're not able to get that, but at least try to have this understanding here. Okay, you just note down how the elements are accessed, how it returns 0.4, 0.5, and 0.6. Okay, so that I will explain in the next slide. Okay. Okay, so you note down here we have d0 into d0 stride and d1 into d1 stride. So meaning that the stride value for dimension 0 is 3. Okay, and then this d1 stride value for dimension 1 is 1. Then I have this d0. D0 is meaning that how many elements are there in d0. So how many elements are there in the d0? It returns there are there are three elements. Okay, we know that there are, from the shape information or size information, we know there are three elements. Okay, similarly, how many elements are there in dimension 1? Okay, so each this is quite, using these words might confuse you. In dim 1 I have three elements. Okay, so no matter which element you pick in dim 0, all of them contains these three elements. Okay, or I would say d1 contains three elements. Okay, then internally make use of this formula to go and pick up the corresponding elements. Okay, so when I create x and pass number 1, then what it actually does is it all the way takes this information and make use of this formula. You see how it makes use of this. Okay, so now I am passing d0 is equal to 1, right? Maybe the next slides might help you. This is d0. I am not passing anything for dimension 1. Okay, in other words, we could have passed something like this 1 comma 0, right? So here we say this is the index for dimension 0, this is the index for dimension 1. So visually what it does is it goes to this element, which is the first element in dimension 0, and then take the 0th element, which means the element at 0th index, from the retrieved element, which is 0.4. Okay, so this makes sense. But if you don't pass this information, when it has only this information, then it says we put d0 is equal to 1, and d0 stride, dimension 0 stride value is 3, so 1 into 3. Now, since there is no information passed, I mean the index is passed to dimension 1, what happens is that it knows that there are 3 elements in the dimension 1. Then it will vary the values of d1 from 0 to 1, 2. Okay, because it knows there are 3 elements. So initially it puts the value 0 here into d1 stride value is a constant, which is 1. So now it goes here 0.4. Okay, then it will change the value of d1 to 1. Okay, so when it changes the value of d1 to 1, then it goes to the next element, and then it changes the value of d1 to 2, then it goes to the next element. Then it will not, that's all, right? Because the first dimension contains only 3 elements, so it will stop the iteration. Then it packs all these numbers and returns it to the user. Okay, so that's how the stride value is internally used to fetch the elements from the respective indices. Okay, so I know this is quite complicated, at least in this case. Whether or are you able to understand this?
Sir, could you please repeat this one more time?
Sure. Okay, so I'm just putting a poll.
Sir, one question.
Yeah.
So here to choose the first element, suppose this is 0.4. So that
Okay.
is that is direct access. But after that it is iteration. Am I right?
Yeah. The reason is that now I am passing the index for dim0, which I am fixing it, right? So the user fixes it, so we can't change that. It is fixed. But for the dim1, the user didn't pass the value, index value. So it iterates over the number of elements in dim1. So it starts from 0, then 1, and then 2.
Okay.
Is this exclusive for Tensor, or is this the normal way that things are accessed?
So this is normal. Even in NumPy, they follow the same rule. This is the rule they have to follow. Otherwise, I mean, since we are saying that, right, no matter which dimensional array you are creating, this will be flattened. The corresponding stride values for each dimension will be created. The corresponding shape value, these are all stored, right? These are all metadata. So the multi-dimensional array is flattened and stored in a memory location. When you retrieve it, they make use of these data and then reconstruct, which means they create a logical view and print it.
Okay, so whenever there is a serialization, this happens.
Yeah, it happens in TensorFlow, it happens in NumPy. It is a general way of storing multi-dimensional array. Okay. What is that board? Okay, there are only 4 votes. So I actually created a poll. Okay, so even in the theory course, right? So in week 3, I guess I was keep telling but typically the participation in the live session is quite low. Week 3 is very important week. So you have to put your enormous effort in order to understand the backprop in week 3. If you miss that, then it is very difficult to understand CNN then difficult to understand RNN. Okay, so in the previous batch students, I told the same. Okay, so when they were studying week 3, I told them this is important week, this is important week, pay a lot of attention. But somehow they kind of, okay, they once they get some, overall picture, they feel themselves, okay, that is fine. But the moment they encounter CNN, right, you can't understand the backprop of CNN or RNN without understanding the how backprop works for ANN. Then you have to roll back and then go and study. Okay, there is no way. If you miss the backprop part of NN, there is no way you will learn about the backprop of CNN or RNN or whatever the architecture that comes in the future, transformer or whatever. Okay, so foundational concepts is always inevitable, always boring, always difficult. Okay, no matter which subject you pick up. Okay, when you study data structures, you might have felt very difficult to construct a binary tree by writing a code. Okay, at the first step, it takes a lot of effort to understand, to build binary search tree or binary tree and do traversal. Okay, but if you miss that, then you will face difficulties when you write a code. Okay, even in deep learning, there are deep learning architectures where this hierarchical way of computing gradients are there. But without understanding this binary tree traversal structure, it is very difficult to understand how you know these hierarchical deep learning models are computing gradients. Okay, in order to understand that, you should have good knowledge in ANN. You should have good knowledge in tree traversal algorithms. So these are all kind of interlinked, but for that we have to put a lot of effort. Okay, so there is a saying, right? I'm not sure, every one starts from ground zero. Okay, the only difference that you see between people is that the amount of effort they put in. Okay, so no one can learn anything without putting in required amount of effort. Okay, so I have seen that whenever you stuck at something, you have to roll back and go to the basic, sometimes even to the I still study linear algebra and probability repeatedly because we tend to forget so many things and we tend to miss so many things. And this tensor concept, I'm sure when you build the deep learning model, even if you ignore this at this moment, you will come back and revisit maybe in some later point of time in your life, but you will revisit it for sure. Okay, now we understand the need for stride all this information. Okay, so to get a logical view of an array, we need all this information. Okay, from the physical view. Okay, so it is absolutely all right to view these as rows. Okay, such as something like this. So if you put organized things in this structure, we can clearly see the outer dimension contains 3 elements. So if you relate it with matrix, all these 3 elements are row of a matrix. So I say dim 0 is equal to row. Then we have some numbers. Okay, then you can interpret these numbers as columns. So we can say dim 1 is equal to columns of a matrix. This is absolutely fine. Okay, you can make use of this. But the moment I switch to 3 dimension, 4 dimension, and I want to access elements from particular dimension, then this way of thinking might lead to some mistakes. Okay, but by practice, maybe you feel comfortable with different approaches. But if you want to ensure the way you are accessing elements in a multi-dimensional array is correct, you have to make use of this stride information, and then you have to do some calculations. Okay, yeah. So why we bother about all these things? Typically, when I create an array, usually I'm again starting with two-dimension array. But even if it is multi-dimensional array, we want to carry out some reduction operation, right? Reduction in the sense I want to compute sum across particular dimension, or I want to compute mean across particular dimension, or I want to compute the argmax across particular dimension. So I have to ensure, right, when you deal with multi-dimensional array, just blindly putting sums equal to and the dims equal to 0, dims equal to 1, dims equal to 2, and see what you are getting, ensuring whether the returned array is what you are expected. Okay, so all these things are quite difficult. So unless we have a good grasp on these dimensions of an array, these might lead to errors. Okay, that those errors are unexpected. In the sense, it still reduce the it still compute the sum across particular dimension. You compute everything, it computes the loss. You see a plot, you feel that the loss is decreasing, but no matter what you do, the loss is not decreasing beyond a particular point. But you will never it is impossible to know that you are making a mistake in computing the sum along a particular dimension. This is extremely important, because even someone goes through your code, right? Since if the model throws an error, that is very convenient, we can fix that. Okay, oftentimes it is going to be a syntax error, but if it is a semantic error, then it is very difficult to debug it. Okay, but deep learning is involved with so many kind of random stuffs, so debugging is extremely difficult in deep learning. But if you have understand about these dimensions, you can avoid many unexpected performance errors. Okay, now I have a tensor X. I'm going to do some reduction operations. So in general, in any framework or in any library, these operations are called as reduction. Okay, because it reduces one of the dimensions. Okay, yeah, what really happens when I put some X and then dims equal to 0? So dim 0 contains 3 elements, I know, right? All these 3 elements are of size 1 by 3, 1 by 3, 1 by 3. Now I am telling to add all these elements, okay? Which means internally what I am telling is, I am telling 0.1, 0.2, 0.3 is there. This is the first element in dim 0. Then the second element is 0.4, 0.5, 0.6. And then we have few more, 0.7, 0.8 and 0.9. Okay. Now I am telling it to add all the elements in dim 0. So how do I add it? Okay, even visually, if you try to make sense this operation through visuals, right? Then of course the obvious reason is to add the elements along the columns. Okay, the obvious way of doing is add the elements along the columns. But how do I do that internally? Okay, so internally, once again, it makes use of strides, but I'm not going to go through it in detail because it will take some time and we don't have enough time, but I just illustrate it. Okay, so the immediate thing, I print the shape and then the stride value. The stride is 3, 1. And now remember, D0 contains 3 elements, so it ran from 1, 0 to 1 to 2, and then D1, each element in dimension 1 also contains 3 elements. Okay, so 0, 1, 2, 0, 1, 2. Okay, then I have to make use of the same formula in order to compute the sum. See how this stride is helping to carry out this sum. Okay, visually we can see it is a sum across columns, right? So it starts with 0th dim. Okay, so D0 is 0, and then the stride value is 3 for dimension 0, and then for D1 also it starts with 0, and then the stride value is 1. Okay, then I get the index value 0. Then I use this index to get the element which is 0.1 here. Okay, now the question is whether I should increase the D0 value or D1 value. Okay, so can you guess which value we need to increase, D0 or D1 first? Because now I am passing do summation across dim 0.
Then 0 should be increased. Okay.
Okay, so even if you make a calculation, right, you can immediately see which one has to be increased. Okay, yeah, so again, for some, I'm just going a little bit faster. Okay, D0 is increased, so you get x of 3, which is 0.4. This element is accessed. Remember, now I am accessing an element so that I can add it. Okay, so even if you add column wise, you take this 0.1 and then add with this 0.4 and then add with this 0.7, which happens if I increase D0 to 2. Okay, now I add these elements. Okay, then I will get 1.2. So I create a new array and then put 1.2. Similarly, I change the D1 value, right? Because I have run out of D0 range, then I have to change D1. Then if you change D1, now the index changes. Once again, it is sum across the column. Now it is first column. Then you change value D1 to 2. Then it is sum across second column, 0.3, 0.6, and 0.9. Okay, so I think this is an extra. Okay, so now you can see once again it's a demo that internally, even if you write down all those array, you see sum across rows, sum across columns. Internally, it is sum by using strides, okay, across elements in each of the tensors. Okay, so you make use of this approach, stride and all this shape information whenever you get a doubt. Okay, if you are unsure of what is going on in the reduction operation, or if you want to cross check whether the reduction operation is actually computed correctly, then you have to rely on this stride value. Visuals most often leads to error. Okay, so if you even have a slight doubt, stick with this. Okay,
So this is why in scalar, when we want to sum across columns, so you would x is equal to 0, not x is equal to 1. It may seem counterintuitive, but this is the reason why we say x is equal to 0 when we try to sum across columns, sum across the columns, along the columns, right?
Sorry, I think I might have interchangeably used this term. 0.2, 0.3, yeah, along the columns. Yes. No,
Yeah.
0.1. This is point. So when I say this one, right?
Yeah, we
Yeah,
use
it's
axis
along the columns. Across means
along the columns. I wanted to say along the columns.
Yeah,
we use x is equal to 0. So this is the reason why we want the first value of the stride to change.
Yeah. So we pass this value so that the strides are properly computed. Now you can see when I said dim is equal to 1 or x is equal to 1 in the whatever the library we use, then the formula remains same. Okay, now this dim 0 is fixed, dim 1 is it's a kind of different operation, right? So now the elements are summed, you can see along the rows, right? Along the rows, right? Along the columns. So okay, I might mess up with these things, but the elements in the first row are summed and then incremented, then the elements in the second row are summed and then third row are summed. Okay, and I don't want to go into dim 3 because it is quite involved, but if you want you can refer to this slide later. I'm just skipping. Even without making use of the stride information, now you see the stride information is quite big because now I am actually having this tensor. Okay, it's now kind of big enough, but fortunately we can make use of the square bracket information to distinguish this dimensionality. Okay, it is not that you have 4-dimensional tensor, we can't visualize this. It has nothing to do with the dimension of the universe or dimension of the 3. We can't visualize beyond 3D. That is true in terms of physical world, but in the logical way, even if you have n-dimensional, you can visualize it using the square brackets. Okay, by counting or backtracking these square brackets. Okay, so now I'm not going to discuss about this. Rather, what I want to do is that I want to sum. I have an tensor x. I want to carry out the sum along dimension 2. Okay, so how do I do that? So without looking into the stride values, visually I can see how things works. Okay, how many elements are there in the dim 0? Can
2.
Okay, there are 2 elements. What is the shape of these 2 elements? Okay, so is everything fine so far? Were you able to follow to this point?
So their shape should be 2, 3, 2, right?
Sorry?
Their shapes, like the
Yeah,
shape.
you're right. 2, 3, 2, yes. Okay, so this is a question to everyone. Is everything is fine so far because this dimension is extremely important.
Yes, sir.
Yes, sir.
Yeah. So also sitting and listening to this, we are kind of moving very slow, but since it is important, I'm just stressing on this again and again. Okay, now I know that in dim 0 I have two elements. Each of the elements are of size 2 by 3 by 2. So visually, somehow this frameworks have not only this framework, this displaying this, right? We can clearly see this. This is one of the element, maybe the first element in dim 0. This is 0th element in dim 0. I can clearly see that, right? Okay. And it says each of the size is 2 by 3 by 2. So if you just move into that, I can verify that. But overall, I know it contains 2 by 3 by 2 elements. Okay. And similarly, if we move on to dim 1, I have 3 by, again, dim 1 contains 2 elements. The size or shape of these elements is, each of these elements is of size 3 by 2, which I can clearly see from here. Okay. There are 3 elements. Each of these are of size 2. So that is why it is 3 by 2. Okay, so again I move into another dimension, which is dim 2. The moment I move into dim 2, what I can see is that I have 3 elements in dim 2, each of size 1 by 2. Okay, that's why we have 3 by 2. Okay, so when I put dims equal to 2, what I am instructing the interpreter is that add the elements along the dim 2. So how many elements are there? There are 3 elements in dim 2. Of course, we have these things, but just now we look into that. Okay, I have 3 elements, each of size 1 by 2. Now I am telling it to add this. It is immediately like I have 0, 2. I took all these 3 elements, 1, 1, and then 0, 2. These are all the 3 elements. Then what is the logical way of adding this? How do you add this? Remember, you can't add 0 plus 2, 1 plus 1, 0 plus 1. Because
Vector
Column
addition.
is
Vector addition.
it's element wise, right? So I have 0, 2, 1, 1, 0, 1. There is no way adding square bracket means doesn't make sense, right? So I have to add the elements element wise. Okay, I add 0 to 1 and then 1 to 0 and then 2 plus 1 and then 1 plus 2. Okay, that is the only possible way. There is no other way. Okay, so I do this and I have some value, and then similarly I repeat for the rest of the elements. Okay, because I have to keep track of all the elements. So I move to the element the same size residing in the other dimension, and then I repeat the same here and I repeat the same here. Okay, so yeah. So if I add this, what will be the output then? Let's try to decode it. So if I add this 0, 1, so the output is going to be 1, 5, right? And for this one, it is going to be 3, 5. And this one is going to be 4, 2. And then this one is going to be 2, 5. Okay, and all of them are packed by following the same dimensionalities. Okay, so it is not you are taking all these elements individually and packing them together. So this is a reduction operation. After this summation, this 3 will disappear because I reduced all these 3 into one single element. Okay, I combined all these 3. Finally, I got only 1 out of these 3 elements. Okay, so which means I essentially removed that dimension. Okay. Okay, so stride value, I'm just ignoring it. You can do this using stride value as well, but once again, I'm ignoring this. Okay. Yeah. So here you can see that if I do summation across this dim 2, you see the resulting matrix or resulting tensor piece of size 2 by 2 by 2, 3 disappeared because this is a reduction operation, so that particular dimension will disappear. Okay, then if you change dim to 1, can you make sense of this output? What really happened? Take your time and you just tell me what are all the elements are and what is the way of adding elements. So in dim 1, how many elements I have? In dim 1 we have 2 elements, each of size 1 by 3 by 2, right?
Yes, sir.
Yes, sir.
Okay, which means I take these elements, right? 1 by 3 by 2. Okay, this one and then this one, the same shape. Okay, now I have only 2 elements to add, each of size 1 by 3 by 2, 1 by 3 by 2. Then how do you add this? Once again, you have to do this element wise, right? We have no other way. So you add 0 to the 1, so you will get 1. Then you add 2 to 2, then you get 4. Then you add 1 to 1, you get 2. Then you add 1 to 2, you get 3. And then 2 to 1, you get 3. And then 0 to 1, you get 1. Similarly, I have 2 more elements because I have to go back to all the way up to dim 0. Then I repeat the same for the element here. Okay, then you can cross check 2 plus 0, 2, all these things. Okay, similarly, you said dim is equal to 3, which means now you are moving all the way up to this 0, 1, 2, 3. Okay, so can you see what really happened? Now my dim 3 contains how many elements? 2 elements, each of size dim 0, right? Now I add this, you can say row wise. Okay, 0, 2, 1, 1, 2, 0, 2. So 2, 2, 2, and then 1, 2, 1, 2, 1, 1, 3, 3, 2, and then 2, 0, 0, 1, 2, 1, which is 2, 1, 3, right? 2, 1, 3, and then 0, 1, 1, 2, 1, 2. So 1, 3, 3. Okay, so this sum, one thing, of course, you can verify whether your output is right or wrong by looking at the shape of the return tensor. That is great if the tensor you are dealing with is of different size along different dimension. But if your batch size, sample size all happens to be kind of same, then you have to rely on your stride calculation, or once you work out deal with many different types of tensor and practice a lot, then you figure out. Okay, it happens intuitively, you build an idea how things are happening. Okay, but it is very difficult to explain it to other. Even if you build an idea intuitively, somehow, unless otherwise we practice, no one can build this intuition. But I hope now we are able to follow up. If we have a multi-dimensional tensor, how things can happen, right? Now, what are all the other options? Instead of sum, I could have used argmax, right? Once again, when I have a tensor, you have to pass the dimension information. Along which axis I have to do this maximum stuff. So if I do dim3, the argmax will return 2, 1, the index, in the sense it's 1. If it is 1, it's 0, 1, like. So the maximum operation again is a reduction operation, right? So it has to be, of course, when we build a neural network, when we pass softmax, internally it computes this argmax for the tensor across batches, right? You might wonder, do we really deal with multi-dimensional array when we build a network? Of course, yes. We don't pass a single element or single sample to the neural network. We pass some 1,000 samples at a time by packing them into batches. For all these 1,000 samples, it will produce 1,000 outputs, each of size, each, 1,000 outputs, each element are going to be a one hot encoded vector or the prediction by the network, which of size 1 by number of classes. So again, we are dealing with multi-dimensional array. Okay, so this is extremely important. Oftentimes you end up messing up with dimension. So to fix that, you should know how things are working across the dimension. Okay, so That's why we need to spend more than an hour on this single concept. Okay, so I hope you all get some idea about this dimension. So you do practice, then you will get a lot of ideas. Okay. Yeah, so we are reaching the end of time. So what I'm going to do is that I'm going to use my collab, which I shared in the GitHub, so you can download it and then practice it. Okay, so these are all the concepts that we have discussed so far. Yeah, now I am creating a tensor of size three-dimensional tensor with 2 by 2 by 2 shape. Okay, so now you can see all these things. So I think this got disconnected. I'm very sorry about that. Okay. So since the outputs are already displayed here, I just walk across this collab. Okay, I'm not going to execute this. Yeah, you can get this stride information for any tensor you created in PyTorch using x.stride. Okay, so make use of this info when you have some doubts. Okay, and I also mention how to calculate stride manually, but that's not required. Then I'm creating a tensor of size 2 by 2 by 2. Of course, so when you stuck with something, you create a smaller size of your problem, right? A toy problem with smaller dimension, which are interpretable or manually workable, and then work with that, so you will get a better idea. Okay, so here you can see a tensor of 2 by 2 by 2 by 2, which is what I displayed in this slide. You get all those info. Yeah, so the physical representations tried, so the same thing, the why we go about all these things, right? So if I want to get the diagonal elements of 1 million 1000 by 1000 matrix, I don't need to even loop across it. So I can, of course, you can call this diag built-in function, which is not actually going through each element in a matrix and checking whether I is equal to j to decide whether it is a diagonal element or not. It actually makes use of this stride information. Okay, yeah, I will share the link. So by making use of this stride information, it simply takes out the diagonal elements in, if I have n by n matrix, if I use stride information, then it will use only n operations, not n square operation, in case if I use the for loop, right? So these are all, of course, efficient. Okay, and you can, if there is a case, if you want to access a diagonal element, you can do that. Okay, so I asked you to do some exercise, you can do that. And there are few more things in this collab which you may come back and revisit after these workshops, then only it makes sense. Okay, so do not try to make sense of what really happens when you copy a tensor. Okay, and keep this in mind, copying is also a costlier operation, because if I load, say, thousands of samples into a memory, for some reason I want to copy that tensor, then by default, if you assign x equal to y, it won't copy. Okay, so I have, say, for example, I have an tensor x, okay, which is loaded using some data set I stored in a variable x. For some reason, I want to manipulate it. I am converting x. I am assigning, sorry, y is equal to x. Okay, and most likely you are already aware of that. It won't make a copy. It don't move the element into a second memory location. It creates a view. Okay, so if you disturb one, the other will get disturbed. Same thing is true when you convert between numpy array to torch tensor. Okay, it won't create copy. It's kind of, it follows some strategy like making use of intermediate buffer, all these things. But you may pay attention to those details, especially when you really need to make a copy of your tensor. Okay, so if you really want to make a copy of your tensor, then you can use a method called as clone. Okay, okay, yeah, something that I just discussed now across a dimension. I have one interesting example at the end. Okay, so when you carry out matrix multiplication with tensor of size 2 by 2 by 2 by 4, I know there is a matrix inside it of size 2 by 4. I just want to carry out the matrix multiplication between 2 by 4 of this tensor and 2/4 of other tensor, I can do that. Okay, and transposing, yeah, here I, for just for demonstration purpose, we know, right, image is an 3-dimensional tensor with RGB values. Suppose if I want to transpose this image, right, you can see that I loaded this image and displayed it. This is actually 1000 by 700 something size, which contains 3 channels RGB. If I want, as mentioned here, if I want to transpose this, how do I transpose this? If you really want to because now if you want to transpose, you have to transpose all 3 channels together, right? So if you simply calling timage.transpose, which is PyTorch inbuilt, this is not we actually want, right? So we have to, even though it is inbuilt, by simply calling transpose on a multi-dimensional array will not work as we expect. Okay, so you have to be aware of what you are doing. Okay, so I want to transpose the entire image, which means I have to transpose all the tensor, right? So for that I have to, work like this. I have to mention the dimension, what are all the dimension I want to transpose. So I am calling this transpose function, and now I'm mentioning which are all the dimension I want to transpose. Okay, of course you take a look, you will understand. Okay, so what it returns, all these things. Okay, so this is one reasonable example. So here also we are doing the same thing in a different way. I'm just passing the order of the dimensions. Okay, so ultimately what I want to convey is that dimension matters. Get a good grasp on this dimension, because we are going to process with multi-dimensional tensors very often. Okay, occasionally or very rarely we deal with simple tensor. It is always going to be 4-dimensional or 5-dimensional tensor in the case of NLP. Okay, so their dim information is extremely important. So in the upcoming workshop, you may say I am putting dims equal to 0, dims equal to 1 in the code, but I won't explain it there. Okay, because that itself take a lot of time if we try explaining why dims equal to 0 is there. Okay, that I want you to understand on your own, given that you have listened to this particular session. Okay, now I think I have covered enough. Yeah. So are you which one? Okay, yeah, you can, if I see some tensor like this 3/5/5, for visual purpose you can think of, in 0 dimension I have 3 elements. Each elements in 0 dimension is 5/5/5, but thinking of using cubes, this is not kind of required at all. Okay, so you do not try to think it as a matrix, do not try to think it as a cube. Rather than doing that, try to think in terms of strides and build an intuition by solving different types of, you create your own tensor and try to interpret it and build an intuition. Okay, that is best, rather than trying to visualize it. Okay, so that's kind of difficult thing to do. Okay, and finally I want to end up this thing with few things. So these are all very important thing in practice. Okay, so when you convert a NumPy array to torch tensor, which we often do, you don't think it is actually creating a copy. Okay, which means they are actually interacting with the same buffer. It is like, you just imagine I have some memory location. Okay, and I have NumPy here and I have PyTorch tensor here. Then when I load a data, these data are residing at here. Okay, so before, actually buffer means before moving on to original memory, there is some intermediate stage. Okay, and then when I ask it to convert into a tensor, actually it also make a view with this buffer. Okay, which means essentially they are accessing the same elements stored at the memory location. Which means if you change one thing here, it will reflect here. If you change one thing here, it will get reflected here. Okay, so those things might cause unexpected, errors or performance degradation. Okay, oftentimes it raises a warning. Okay, so when the framework itself raises a warning, pay attention to it, don't ignore it. Okay, that might cause potential problems after, we may not realize it until we train it. Okay, yeah, we can do in place operation, but in place operation is not recommended. Okay, because now it is not just tensor. We are creating we need some gradients for the tensors as well. When you make an in place operation, then the gradients will get affected. Okay, this is really complicated when it is not just that easy. Okay, so avoid in place operations as much as possible. If you are doing in place operation for some reason, ensure that while gradient is computed, which I will talk in the next session, how gradients are actually computed. Ensure that you understand how the gradients are computed, and in place operation is not affecting that gradient, or it is what you are actually expecting. Okay, these are all, these two are extremely important. Okay, so yeah, it's quite
Sir, we
involved.
don't have access to this collab. Can you please share that?
Yeah, give me a second. Yeah, that's all with today's content. I know it is quite high. Even for me, if I sit in some session, listening continuously for 2 hours is not possible. So if possible, you rewatch this session or practice with the collab. Okay, I'm sharing that. Yeah, so I shared it in the chat box. Please check whether you are able to access that. And of course, I have already shared some of the collabs which I will use in the subsequent sessions. If you have time, you go through it. I try to, I have given enough explanation in the collab itself. If you are able to understand that, that's fine. If you have doubts, you can note it. It is always good to go through the collabs before coming to the session, so that you can get your doubts cleared. Okay, that's all for today. So if you have any questions, let's discuss. Otherwise, we can wrap up the session and see you tomorrow.